All right, everybody. Today we're going to start Unit 11. So this is thermal chemistry. So all thermal chemistry is it's the study of energy changes that occur during a chemical reaction. So we've talked about this before. Every time a chemical reaction takes place, there is a change in energy. Some reactions are going to release energy. Some reactions are going to take in energy. But thermal chemistry is the study of this process and tracking where the energy goes and what happens to that energy. So there's a few things we need to talk about when we start to understand the flow of energy. So this first one is something we have talked about before, the first law of thermodynamics, which simply states that energy cannot be created or destroyed, only changed forms. And so we've talked about potential energy, we've talked about kinetic energy. Here we're going to also look at chemical energy. So the energy that can be stored in the bonds of a molecule or in the bonding of an atom that can then be released back out into its surroundings. The second thing is our second law of thermodynamics. Energy spontaneously flows from areas of high to areas of low. So essentially what this means is our energy is going to travel from hot things into cold things without any help at all. And so heat always travels to cold, energy always flows to where there is lack of energy. Same kind of principle as when we talked about diffusion in our gas laws. And the last term we need to know before we get started is enthalpy. Enthalpy is just a measure of the change of energy of a system. We're going to see it represented by a delta H to show us that we have change. So big thing that we talked about a long time ago is the difference between heat and temperature. So when we talk about heat, we are talking about an energy source. Okay, so where our energy is going to flow from hotter regions to cooler regions. We're going to refer to this in terms of joules, or like we did in our lab yesterday in terms of calories. Okay, those are units of energy. When we talk about temperature, okay, temperature is a measurement. And so this is degrees of hotness or degrees of coolness. Okay, it is a measure of the average kinetic energy of that system that it's measuring. And so this is where we're going to use Kelvin or we're going to use Celsius. Okay, when we increase energy, we're going to see an increase in the heat, we're going to see an increase in the temperature. When we decrease energy, we're going to see a decrease in our temperature. So heat is the energy, temperature is the measurement of that energy, or the measurement of those molecules moving. So here we can see that delta H is a change in enthalpy from reactants to products. So we stated every single chemical reaction is going to involve a release or an absorption of energy in some form or fashion. So when we break chemical bonds, we need to put energy in for that to happen. So when we have energy going into a system, we are going to call that endothermic. So our heat, our temperature is going into that system. If we have bonds that are being formed, okay, bonds that are being formed are going to release energy out. And so what we're going to find when we are leaving, it's going to be exo. So the heat, the energy is leaving. And so endothermic, where we're taking in energy, is going to have a positive delta H. Exothermic is going to have a negative delta H. And so when we talk about endothermic versus exothermic, there's something that will keep coming back up, and that is the system versus the surroundings. And so these are two different things that we need to define. And so my system could be a beaker of water. My surroundings is technically everything else in the universe outside of that beaker of water. But when we're really looking at identifying a system and its surroundings, while your surroundings can be everything, generally we're going to specify them. And so if you think about the nut lab, okay, our burning of the nut, that was our system, okay? We collected that heat, we collected that energy in our beaker of water. So my nut was burning, it was releasing energy into its surroundings. We were able to measure how much we put in surroundings by looking at that water. And so it's very, very important when we're looking at change that we identify what is the system, what are the surroundings, where is the energy moving from, where is the energy moving to. So when we look at endothermic, so we are putting energy in. Okay, what this is going to do is it's going to move us from a solid to a liquid to a gas in terms of states of matter. The more energy we put in, the more excited those molecules get, the higher up we move in our states of matter. Okay, when we think about endothermic, this one goes a little bit against maybe what our head would tell us. If we're putting energy into it, okay, we would maybe think that it's going to be hot, but we're really going to feel cold. And the reason why we feel cold is because in an endothermic reaction, it is absorbing heat from the surroundings. So we're not touching the solution, we'd be touching the outside of the beaker. The beaker is going to feel cold because it is taking heat out of the beaker to put it inside of itself. And then we're going to see something that looks like this energy diagram here. Okay, and what we look at is we look at our reactants and our products, and we look at how those two things change. And so in a chemical reaction, we're always going to have something called an activation curve. Okay, so we're going to have a nice point where this is the amount of energy needed for the reaction to take place, and then we're going to change to a different amount of energy. When our energy of our products is higher than the energy of our reactants, that's going to tell us endothermic. It took on energy. When we think about exothermic, okay, exothermic is pulling energy out. So that would be the reverse, where we'd move from a gas to a liquid and then to a solid. And because we're taking energy out, if you were to hold a beaker that had an exothermic reaction taking place, it would feel warm to the touch because that solution is putting out heat, putting out energy into our surroundings. And now when we look at our energy diagram, okay, we can see that we've got our reactants, we still have our activation energy, we've got our high point. But when we look at this, now we've got our products below. And so energy went out, and we know that we are going to have a exothermic reaction. Okay, exothermic gives us a negative delta H. Endothermic gives us a positive delta H. So when we look at exothermic versus endothermic, okay, making an ice cube. So we're going from a liquid to a solid, we have to pull away heat. But when we go from an ice cube to a liquid, okay, we are putting energy into it to heat it up, to get it to melt. And so as we kind of go down and we look at all these things, okay, our exothermic processes are going to be moving us towards something more solid. Okay, it's going to be forming new bonds that we can then release energy out into the system. When we look at endothermic, okay, we are looking at putting energy in. And so we're changing states, going up. This would be things like cooking, so baking bread, cooking eggs. Okay, we are changing those proteins. We are cooking those things with heat. So those would be endothermic processes. So anytime we form stuff, it's exothermic. Anytime we're breaking stuff down, that's going to be our endothermic. So here we've got a better look at our energy of a reaction. And so you can still see on both sides, we've got reactants. Okay, we've got our energy going up the side. We've got our activation energy on both of these. And so what we can see there is that as we reach our activation energy, we're going to drop back downhill. And depending on if we drop below our reactants or we're above our reactants, is going to tell us if we've got an endothermic or exothermic. Remember, endothermic, we're absorbing energy. Exothermic, we are releasing energy.